السلام عليكم ورحمة الله وبركاته. بسم الله الرحمن الرحيم. الحمد لله رب العالمين، والصلاة والسلام على أشرف الأنبياء والمرسلين سيدنا محمد وعلى آله وصحبه أجمعين. This is a video recording for the learning activity on respiratory physiology under special conditions in the respiratory block. Here we have the intended learning outcomes, the ILOs for this learning activity, and these are the recommended learning resources for the learning activity. In this learning activity, we shall describe respiratory physiology under three special conditions, including breathing high oxygen, hypobaria, and hyperbaria. And let's begin with the respiratory physiology when we breathe high oxygen. This might result in oxygen toxicity because breathing high oxygen might lead to the production of free radicals, especially superoxide, and this superoxide might result in dysfunction of the enzymes and also macrophage dysfunction. It has been found that if we breathe 100% oxygen for approximately 48 hours, this can damage the lungs, leading to acute respiratory distress syndrome. And it has been also found that if we are exposed to partial pressures of oxygen which are higher than the atmospheric pressure, higher than 760 millimeters of mercury, this might lead to central nervous system signs and symptoms, including convulsions in the form of tonic-clonic convulsions or grand mal seizures. We are finished with the breathing high oxygen, and now let's move on and describe hypobaria. Hypo means low, and baria refers to the atmospheric pressure. So barometric pressure, as you all know, is 760 millimeters of mercury at the sea level, but this barometric or atmospheric pressure decreases with distance above the sea level. It decreases with altitude. Remember, this atmospheric pressure is because of the weight of the gases of the atmosphere. So as we ascend high, the thickness, if you like, of the atmosphere which surrounds Earth becomes less, and hence the weight of the atmosphere becomes less, and accordingly the pressure becomes less, because the pressure is the weight over the surface area. At the sea level, where the barometric pressure, the atmospheric pressure, is 760 millimeters of mercury, the partial pressure of oxygen in the atmosphere would be equivalent to 760 millimeters of mercury, which is the atmospheric pressure, multiplied by 0.21, which is 21%. This is the fractional concentration of oxygen in the atmosphere. Thus, the partial pressure of oxygen in the atmosphere at the sea level is 160 millimeters of mercury in dry air. Now, as we ascend high, because the barometric pressure decreases while the fractional concentration of oxygen remains the same, which is 21%, thus the partial pressure of oxygen decreases. So, for example, at 5,430 feet in Denver, for example, where the barometric pressure is now 625 millimeters of mercury, the partial pressure of oxygen in the atmosphere would be 131 millimeters of mercury, and so on. So at a height of 29,000 feet, which is the Mountain Everest, the barometric pressure is only 250 millimeters of mercury. At the sea level, it is 760, while at 29,000 feet, it is only 250 millimeters of mercury, and at this height the partial pressure of oxygen in the atmosphere is only 53 millimeters of mercury. In commercial airlines, the cabin pressure at approximately 4,000 feet, where the barometric pressure is 565 millimeters of mercury, is 118 millimeters of mercury. It is thus evident that higher altitude results in lowered availability of oxygen and hence hypoxia. The type of hypoxia which we develop at high altitude is known as hypoxic hypoxia. Now, this hypoxia develops because the barometric pressure is decreased as we ascend at high altitude, and the decrease in the barometric pressure causes a decrease in the partial pressure of oxygen in the alveolar air, and this will eventually lead to a decrease in the partial pressure of oxygen in the arterial blood, which we call hypoxemia. In this figure we have here our barometer. So it is because of the weight of the gases of the atmosphere, pressure is exerted on the surface of mercury, and mercury then ascends in this column, in this tube, and at the sea level the barometric pressure or the atmospheric pressure is, as we mentioned in the previous slide, is 760 millimeters of mercury, and at this barometric pressure the partial pressure of oxygen is 160 millimeters of mercury in dry air. And again, as we ascend higher and higher, the barometric pressure gets lower and lower, and the partial pressure of oxygen is lower. However, the fractional concentration of oxygen doesn't change. It remains the same whether we are at the sea level or whether we ascend at high altitude. What changes is the barometric pressure, the total barometric pressure, and not the fractional concentrations of the gases which we have in the atmosphere. Now, the primary problem which develops when we ascend to high altitude, as we've mentioned, is hypoxemia. Now, in this diagram, on the x-axis we have the altitude in feet, and on the y-axis we have the pressures. So the red curve, this is the barometric pressure curve as we ascend to high altitude. So at zero altitude, which is the sea level, the barometric pressure is 760 millimeters of mercury. As we ascend to high altitude, the barometric pressure decreases as seen in this curve. The curve which is blue in color represents the partial pressure of oxygen in the inspired air in the atmosphere. So at the sea level, when the atmosphere is dry, the partial pressure of oxygen in the atmosphere is 160 millimeters of mercury, as we mentioned in the previous slides, and as we ascend to high altitude, the partial pressure of oxygen decreases. The decrease in the partial pressure of oxygen in the atmosphere is associated with a decrease in the partial pressure of oxygen in the alveolar air. So at the sea level, where the barometric pressure is 760 millimeters of mercury and the partial pressure of oxygen in the atmosphere is 160 millimeters of mercury, the partial pressure of oxygen in the alveolar gas in the alveolar air is 100 millimeters of mercury, and as we ascend to high altitude it decreases. What happens to the partial pressure of carbon dioxide? Well, this is not significant. The change is not significant, and the primary problem again which arises as we ascend to high altitude is acute hypoxemia. So then the body then needs to acclimatize to high altitude. Our body acclimatizes to high altitude by hyperapnea, polycythemia, and by increasing the formation of 2,3-biphosphoglycerate, which is also known as 2,3-diphosphoglycerate, and by other responses which we will describe briefly during this learning activity. So the first acclimatization process, or the first compensatory process to high altitude, if you like, is hyperapnea. So in response to hypoxemia, the ventilation is stimulated as a result of stimulation of the peripheral chemoreceptors. The developed hyperapnea as a result of the hypoxemia of the high altitude causes increased exhalation of carbon dioxide. Accordingly, the partial pressure of carbon dioxide in the arterial blood decreases, and such decrease in the partial pressure of carbon dioxide in the arterial blood causes increase in the pH of the arterial blood, and this condition is what is known as respiratory alkalosis. And in respiratory alkalosis, the central chemoreceptors are inhibited, causing a decrease in the ventilatory response. In response to the developed respiratory alkalosis, the body develops other compensatory mechanisms in the form of less reabsorption of bicarbonate ions and secretion of more hydrogen ions by the kidneys, and this developed compensatory mechanism by the kidneys return back the pH of the arterial blood towards the normal value, while the arterial partial pressure of oxygen is still low because of the high altitude. And as a result of this renal compensatory mechanism to respiratory alkalosis, hyperapnea is allowed to resume again. The other acclimatization process which the body develops as we ascend to high altitude is polycythemia, because hypoxemia causes stimulation of the release of erythropoietin from the kidneys, and erythropoietin stimulates the bone marrow to produce more red blood cells. Hence, the concentration of hemoglobin increases, and it increases from 15 to 22 grams in each 100 milliliters of the blood. And the increase in the hemoglobin concentration, it obviously increases the oxygen carrying capacity of the blood and the oxygen content of the blood, and there is also increase in the diffusion capacity of oxygen. However, polycythemia has side effects, and the side effects of polycythemia include increase in blood viscosity, because the viscosity of the blood is primarily due to the red blood cells and due to the plasma proteins. And polycythemia can also result in blood clots. The increase in blood viscosity because of polycythemia can lead to an increase in blood pressure. There is also increase in the formation of 2,3-biphosphoglycerate or 2,3-DPG as we ascend to high altitude in response to hypoxemia. And 2,3-DPG, as we described in other learning activities, causes a right shift in the oxygen hemoglobin association curve, because 2,3-DPG decreases the affinity of hemoglobin for binding oxygen, and this is beneficial at the tissues because it results in easier unloading of oxygen from hemoglobin to the tissues, but it is not good at the lungs because it would be harder for hemoglobin to be reoxygenated or to be loaded with oxygen in the lungs in the presence of high 3 dBg in the red blood cells. Other responses which the body develops when we ascend to high altitude, we call it natural acclimatization processes or responses. These include increased vascularity and more efficient and plentiful mitochondria and oxidative mechanisms, increased chest size, smaller mass of the body, and larger right ventricle. When we ascend to high altitude, some people might develop altitude sickness. This altitude sickness includes acute mountain sickness, and it might also lead to very serious pathophysiological conditions like high altitude pulmonary edema and high altitude cerebral edema. So what is then acute mountain sickness? Acute mountain sickness might develop in people who ascend to high altitude and can begin to occur at altitudes beyond 8,000 feet, and it varies with the rapidity of the ascent and the time which is spent at a given altitude. However, the age, the gender, and the physical fitness have no influence on the development of acute mountain sickness. It can occur anywhere from a few hours to 24 hours after arrival to an elevated altitude, and the clinical picture, the symptoms and signs which are seen in acute mountain sickness, they are because of the hypoxemia and respiratory alkalosis that develops due to hyperapnea, and include headache, fatigue, dizziness, nausea, sleep disturbances in the form of insomnia, peripheral edema, and in the minority, some serious complications of high altitude pulmonary edema and high altitude cerebral edema might develop. So how can we then prevent the development of acute mountain sickness? There are some precautions which should be taken in order to prevent the development of acute mountain sickness, including gradual ascent in order to promote acclimatization. One should not ascend more than 1,000 feet in a day, and he should take rest a day after 3 days, and he might also, or she might also, take some prophylactic drugs in the form of acetazolamide and dexamethasone. Now, the serious complications of acute mountain sickness include high altitude pulmonary edema and high altitude cerebral edema. The high altitude pulmonary edema symptoms usually manifest within 12 to 96 hours, and there are some major predisposing factors to the development of high altitude pulmonary edema, and these major predisposing factors include the level of the altitude. So it occurs at altitudes above 10,000 feet, the rapidity of the ascent, and there is also some individual predisposition. It occurs in about 2% of the people who ascend to high altitude. Pathophysiologically, there is pulmonary vasoconstriction leading to an increased pressure, and the increased pressure in the pulmonary circulation favors the filtration of fluid into the alveoli, leading to pulmonary edema with subsequent poor exchange of gases and hypoxemia and hypercapnia. The symptoms of high altitude pulmonary edema include dyspnea, which is difficulty in breathing, marked fatigue, confusion, and it is a serious complication of acute mountain sickness, which could be potentially fatal. How would we treat someone who develops high altitude pulmonary edema? Descent, supplemental oxygen, and the calcium channel blocker nifedipine, which causes relaxation of the smooth muscle cells of the arterioles in the pulmonary circulation, leading to vasodilatation and reduction in the pulmonary artery pressure. Another very serious complication of the acute mountain sickness is the high altitude cerebral edema, and again the symptoms usually manifest within 12 to 96 hours like high altitude pulmonary edema, and there are major predisposing factors which predispose to the development of high altitude cerebral edema, including the level of the altitude. It occurs at altitudes above 10,000 feet, similar to the high altitude pulmonary edema. Also, rapidity of ascent is another major predisposing factors, and there is also individual predisposition. And high altitude cerebral edema occurs in approximately 1% of the people who ascend to high altitude, while high altitude pulmonary edema occurs in about 2% of people. Pathophysiologically, there is increased leakiness of the capillaries of the blood-brain barrier. The reason for this increased leakiness or permeability of the capillaries of the blood-brain barrier is not fully understood, but the result is fluid and protein leak into the brain and cerebral edema. Clinical picture include severe headache, loss of coordination, hallucination, memory loss, and it is again a very serious complication of acute mountain sickness and can lead to coma and death. Treatment similar to high altitude pulmonary edema descent: supplemental oxygen, acetazolamide, this is a diuretic, and dexamethasone. We've been describing acute mountain sickness, and people who live at high altitude for after several decades might develop a condition known as chronic mountain sickness. So what is chronic mountain sickness? It is a rare syndrome which occurs in long-term residents at high altitude after several decades. Chronic mountain sickness is associated with polycythemia, congested cheeks and earlobes, cyanosis, clubbing of the fingers, and right ventricular enlargement, and it is a gradually progressive condition. We have finished with hypobaric physiology, and let's now describe hyperbaric physiology. Hyperbaric relating to producing, operating, or occurring at pressures higher than the normal atmospheric pressure. Hyper means higher than normal, and baric refers to the atmospheric pressure. So when are we exposed to hyperbaric conditions? We are exposed to pressures higher than the atmospheric pressure, for example during diving. So every 33 feet below water results in an increase of 1 atmosphere. So at the sea level, at the surface of water, the pressure is 1 atmospheric pressure. Now if we dive 33 feet below the surface of water, the pressure becomes 2 atmosphere, which is 1 original atmospheric pressure plus the 1 additional atmosphere because of the 33 feet diving. At 66 feet, the pressure would be 3 atmospheric pressures, the 1 original, and 2 atmospheres because we are now at 66 feet below the surface of water. We can also be exposed to pressures higher than the atmospheric pressures when we are in hyperbaric chambers. A hyperbaric chamber is airtight chamber pressurized with air, and the hyperbaric chambers which are commonly used utilize an absolute pressure of 2 atmosphere and 100% oxygen for 1 to 2 hours. We might use this concept in hyperbaric oxygen therapy, which involves the administration of oxygen at pressures greater than the atmospheric pressures, and we place an individual into a hyperbaric chamber. Now, placing an individual into a hyperbaric chamber with oxygen at pressures greater than the atmospheric pressure increases the partial pressure of oxygen based on Dalton's law, and this increases the dissolved oxygen based on Henry's law. This fully saturates hemoglobin and increases the driving force for oxygen delivery to the tissues. This is a hyperbaric oxygen chamber where we use hyperbaric oxygen therapy, and many hospitals are now building up the hyperbaric oxygen chambers for hyperbaric oxygen therapy. Hyperbaric oxygen therapy is beneficial because it results in greatly increased oxygen concentration in all the body tissues, and it might also stimulate the formation of new blood vessels, which we call angiogenesis, to locations with reduced circulation, and this improves blood flow to areas with arterial blockage, and it also stimulates an adaptive increase in the superoxide dismutase enzyme, which is a powerful endogenous antioxidant, and it aids in the treatment of infection by enhancing the action of neutrophils. Now let's describe decompression sickness as a potential problem with hyperbaria. What is decompression sickness? Decompression sickness is a clinical illness that results from the formation of small bubbles of nitrogen gas in the blood and in some tissues of the body as a result of rapid ascent after someone dives. As the diver descends and takes on pressure, the nitrogen is compressed and more of the nitrogen is dissolved into the body fluids based on Henry's law. On rapid ascent, as the pressure decreases, nitrogen comes out from the tissues of the body, and it results in the formation of nitrogen bubbles. Most of these nitrogen bubbles are removed and filtered out by the lungs. However, if these nitrogen bubbles, which are formed as someone ascends after diving, if they develop very quickly, or if they were too numerous, the diver might develop what is known as the bends. What are these, the bends? The bends, this is a slang term used for decompression sickness. So the nitrogen bubbles, they become lodged in the small blood vessels and the joints, and this activates a powerful inflammatory response, and it might lead to platelet aggregation, leading to thrombosis with possible embolism. If a small clot is dislodged from a thrombus, it might lead to stroke, heart attack, or pulmonary embolism, and also the nitrogen bubbles might lead to disturbances in the central nervous system if the bubbles cause ischemia to the brain, and these disturbances take the form of impaired vision and even paralysis. That's the end of this learning activity, and here again we have the intended learning outcomes, and thank you very much for your attention and listening.